Hey, it's Weinstein, and today we'll see how polar bear fur inspired warmer materials. Point a thermal camera at a polar bear in the freezing Arctic, and something strange happens. It almost disappears. The snow glows, the air shimmers, but the bear is barely there. Not because it's cold inside, it's warm, very warm, it's because its coat is so good at trapping heat that almost none escapes. This animal wears the best insulation on Earth, and we're only now learning to copy it. The polar bear lives where almost nothing else can. Temperatures plunging to 40 below, wind that cuts like a blade, ice, water, and months of darkness. And through all of it, the bear stays toasty warm under a coat that looks, honestly, kind of ordinary. But that fur is one of the most advanced thermal systems in the natural world. And it hides a secret in every single hair. Think about our best winter gear. Down jackets, synthetic fills, high-tech fleece, decades of engineering to keep us warm. The polar bear beats all of it. Gram for gram, its coat outperforms the insulation humans have spent a century developing. And it does this while staying thin enough to swim in, light enough to run in, and tough enough to survive the Arctic. That's a very hard combination to beat. Back to that thermal camera. A thermal camera doesn't see light, it sees heat radiating off a surface. Most warm things glow brightly on it. You do. Your coffee does. A running car does. But the polar bear barely registers. Its surface stays almost as cold as the snow around it, even though the animal underneath is warm and alive. The heat simply isn't getting out. And that is the whole trick. That's what insulation really means. Not making heat, but stopping it from escaping. Your body makes plenty of heat, so does the bear's. The question is how fast it leaks away. In the Arctic, lose heat too quickly and you die. So the bear's coat is built for one job above all, to slow that leak to a trickle. And to understand how, scientists first had to bust a beautiful myth. For years, there was a lovely explanation for polar bear fur. The hairs are hollow and colorless, and the story went like this. Each hair works like a tiny fiber optic pipe, catching sunlight and channeling it down to the bear's black skin to warm it up. It's elegant, it's memorable, it appeared in textbooks and documentaries for decades. There was just one problem with it. It isn't true. When researchers actually tested it, polar bear hairs turned out to be terrible light pipes. They don't funnel any meaningful amount of sunlight down to the skin. The fiber optic story was beautiful, widely repeated, and simply wrong. But here's the twist that makes this episode honest. Killing the myth revealed something even better. The real secret wasn't about light at all. It was about the shape of the hair. And that matters. Science isn't a collection of pretty stories, it's a process of testing them and dropping the ones that fail. The light pipe idea failed. But instead of a dead end, that opened a door. Because when scientists looked closely at why the hair was hollow, they found a structure that explains the bear's warmth far better than sunlight ever could. So what's actually inside a polar bear hair? Slice a polar bear hair and look at the cross-section, and you'll see it's not solid. It has a hollow core running down the middle, wrapped in a shell of keratin, the same protein in your hair and nails. Scientists call this a core shell structure, an empty channel inside a solid casing. It sounds simple, but that empty space is doing something remarkable. The magic here is literally nothing. Empty space. Here's the first key idea. For trapping heat, hollow beats solid. A solid fiber conducts heat straight through itself from the warm side to the cold side. But a hollow fiber has a pocket of trapped air inside, and air is a lousy conductor of heat. That trapped air blocks the flow. So the hollow hair carries far less heat away from the bear than a solid one would, using less material and less weight. Emptiness doing real work. This is the heart of almost all insulation. Trapped air. Air barely conducts heat as long as it can't move. The problem is that free air flows, carrying warmth away with it. So the goal of any good insulator is to trap air in tiny pockets so it can't circulate. That's what a down jacket does, that's what a wool sweater does. And it's what the hollow core of a polar bear hair does beautifully. Picture the difference between a windy day and a still one at the same temperature. The windy day feels far colder, because moving air strips heat off your skin. Still air is a cozy blanket, moving air is a thief. Good insulation is really just a clever trap for holding air still. The more tiny, sealed pockets of motionless air you can create, the warmer you stay. And nature has a champion at this. That champion is a class of materials called aerogels. An aerogel is a solid that's almost entirely empty space up to 99% air, held in a delicate, sponge-like skeleton of solid material. It's sometimes called frozen smoke because it looks like a faint blue haze you could blow away. And aerogels are the best thermal insulators humans have ever made. The polar bear's hair, it turns out, is nature's version of this idea. Why is aerogel so good? Because it takes the trapped air trick to the absolute extreme. Its structure is riddled with pores so tiny that air molecules inside can barely move at all. The air is trapped in pockets smaller than the distance heat needs to travel to spread, so heat gets stuck again and again at every tiny wall. Almost all air, almost no solid to conduct through, it's about as close to insulating with pure nothing as physics allows. And that's the real punchline about the polar bear. Its hair isn't a light pipe. It's a porous, air-filled, aerogel-like structure, a hollow core plus a spongy, pore-rich shell that traps air on multiple scales. Nature quietly engineered one of the best insulators known, grew it as a hair, and put billions of them on one animal. No sunlight tricks required, just trapped air arranged brilliantly. So naturally, we wanted to copy it. Think about what that hair offers. Incredible warmth, very low weight, and it's thin, not a bulky puffball, but a slender fiber. That combination is an engineer's dream, because our warm clothing tends to be bulky and our thin clothing tends to be cold. A material that's warm and thin and light would change winter gear completely. The challenge was clear. Could we spin a fiber that works like a polar bear hair? In 2018, a team led by the researcher Quay published a paper in the journal Advanced Materials with a very direct title, A Thermally Insulating Textile Inspired by Polar Bear Hair. They didn't just admire the hair, they built an artificial version of it, a fiber with the same hollow, porous, heat-trapping structure. And the way they made it is genuinely clever. It starts, of all things, with freezing. Their method is called free spinning. Here's the idea. You take a liquid solution of polymer, think of a kind of dissolved plastic, and as you push it out into a fiber, you freeze it in a controlled way, from one direction. As it freezes, ice crystals grow through it in orderly lines. Freezing is the sculptor here, and what those growing ice crystals do next is the whole trick. As the ice crystals grow, they shove the polymer aside, forcing it into thin walls between them. Then you remove the ice, and every place a crystal used to be is now an empty pore. What's left is a fiber full of long, aligned, air-filled channels wrapped in a solid shell. In other words, a hollow, porous, core shell fiber, the artificial cousin of a polar bear hair, built by freezing, then emptying, and it worked. The free-spun fiber trapped air just like the bear's hair, and it insulated better than natural down while being thinner. Let that sink in. A lab-made fiber, warmer than the goose down in your best winter coat, in less thickness. All by copying the internal architecture of a single strand of bear fur. Same principle, human-made. But a great fiber in a lab isn't yet a sweater you can live in, because real clothing has to survive real life. It gets stretched, bent, tugged, and stuffed into bags. It gets sweaty and dirty and thrown in the washing machine. An aerogel is famously light and warm, but also famously fragile. Early aerogels could crumble if you looked at them wrong. So a beautiful insulating fiber is one thing. A fiber you can actually wear and wash is a much harder challenge. This is the catch with aerogels. All that empty space that makes them such great insulators also makes them delicate. Squeeze them, stretch them, soak them, and that fragile skeleton can collapse. And once the pores are crushed, the insulation is gone. For decades, that fragility kept aerogels out of everyday clothing. To put a polar bear fiber on your back, someone had to make it tough. And in 2023, someone did. In 2023, a team led by the researcher Wu took the next big step. They engineered a new version of the aerogel fiber that fixed the fragility problem and then some. Their fiber kept the warmth of the polar bear structure, but added something aerogels had never really had: stretch and durability. It was the difference between a lab curiosity and something you could actually knit into a garment. How stretchy? Their fiber could be pulled to 10 times its length, a stretch of 1,000% without losing its insulating properties. Think about that. You can yank it, flex it, move in it, and the tiny air pockets keep doing their job. That's the flexibility of a rubber band with the warmth of an aerogel. For clothing, that's exactly what you need. Insulation that bends and moves with your body. And here's the part that makes it real. You can machine wash it. That sounds mundane, but it's huge. Washability is the line between a science demo and an actual product. A sweater you can't clean is useless. The 2023 fiber survives the washing machine and keeps its warmth. They even knitted it into an actual sweater, a real, wearable garment built on the polar bear's blueprint. Frozen smoke, turned into clothing you can throw in the laundry. Step back and appreciate why warm and thin is such a big deal. Today, to stay warm, you usually go bulky, thick, puffy coats that make you look like a marshmallow and restrict how you move. A fiber this efficient could keep you just as warm in a fraction of the thickness. Sleeker jackets, lighter layers, real freedom of movement in deep cold, warmth without the bulk. That alone would change winter clothing. And it's not just comfort. For anyone who carries their warmth, weight is everything. Mountaineers, soldiers, polar researchers, astronauts, every gram on your back matters when you're moving through extreme cold. A super light insulating fiber means the same warmth for less weight or far more warmth for the same load. In the harshest places on Earth and beyond, that can be the margin between success and failure. But clothing might be the small story here, because the real energy hog isn't what's on your body, it's the building around you. Think about every home, office, school, and shop that has to be heated in winter and cooled in summer. Keeping buildings comfortable is one of the largest uses of energy on the entire planet. And most of that energy is fighting one thing: heat leaking through walls, roofs, and windows. Consider the scale. A huge share of the world's total energy goes into heating and cooling buildings. And a lot of it is simply wasted heat you paid for, escaping through poorly insulated walls into the cold outside. Every drafty wall is money and energy leaking away, every hour of every winter. Better insulation isn't a minor upgrade. On a planetary scale, it's one of the biggest energy levers we have. Now imagine wrapping a building in the same trapped air genius as a polar bear's coat. Aerogel-based insulation panels thin, light, and far better at stopping heat than the foam and fiberglass we use today. A thinner panel that insulates better means walls that lose less heat, buildings that need less energy to stay warm, and lower bills in every unit. The polar bear's trick, scaled up from a hair to a housing block. And thinness matters more than you'd think in construction. Traditional insulation is bulky, thick walls, eat up floor space, and add cost. An aerogel panel that does the same job in a fraction of the thickness means more usable room inside, easier retrofits onto old buildings, and better performance where thick insulation simply won't fit. Warmer buildings, thinner walls, less wasted energy. The same idea that keeps a bear alive could quietly cut the world's heating bill. Stop and take in the range here. The same principle, trap air in a hollow, porous structure, works in a single strand of bear fur, in a stretchy fiber knitted into a sweater, and in a panel bolted onto the side of a skyscraper. From one hair to a whole building. The physics of trapped air doesn't care about scale. Nature proved it on an animal, we're spreading it across our clothing and our cities. And here's the deep lesson. The polar bear's hair isn't made of some miracle substance, it's keratin, the same ordinary protein as a horse's hoof or your own fingernails. What makes it extraordinary is its structure, hollow, porous, full of trapped air. The warmth is in the architecture, not the ingredient. Take an ordinary material and fill it with the right pattern of empty space, and you get one of the best insulators on Earth. Let's be honest though. A stretchy, washable aerogel fiber in a lab and a sweater on a store shelf are not the same thing. Scaling this up, making it cheaply, in huge quantities, reliably, at a price people will pay, is a serious challenge. The same goes for wrapping whole buildings in aerogel panels. Cost and manufacturing are real hurdles. Nature gave us the principle and the proof. Turning it into products is years of hard work. And there are wrinkles. Aerogel fibers must be tuned for durability, moisture resistance, and cost all at once. A building panel has to be fireproof, weatherproof, and affordable, not just warm. Manufacturing has to go from a lab bench to a factory line. Scientists and engineers are working through exactly these problems right now. Progress is real, but the road from a knitted demo sweater to your closet and your walls still runs ahead. And that's completely normal. The polar bear was solving its own problem, surviving the Arctic, not designing our jackets or our buildings. Our job is to spot the principle in its hair and adapt it to our needs. The idea of a hollow, air-trapping, aerogel-like fiber turned out to be priceless. The details, durability, cost, scale, are for engineers to work out, application by application. That's how good ideas travel from nature to us. So what do we actually take from the polar bear? Not its hair and not its keratin. We took the architecture, a hollow core wrapped in a porous shell, trapping still air on many scales the way an aerogel does. That idea is now being free-spun into fibers, stretched, washed, knitted, and someday bolted onto buildings, a blueprint from a single strand of Arctic fur spreading into our coats and our walls. So the polar bear, it turns out, is a brilliant thermal engineer, It solved a problem we struggle with: how to be warm, thin, and light all at once, and it solved it elegantly, with nothing but cleverly arranged empty space. And it's been doing this for a very long time, long before the first down jacket or fiberglass wall. Once again, nature got there first out on the Arctic ice. And this changes how you see the animal. A polar bear looks like a big warm rug that happens to walk. But every hair on it is a precision insulation device, an aerogel grown as fur, invisible to heat cameras, keeping a warm-blooded giant alive at 40 below. Hidden in that familiar white coat is a material science lesson we're only now learning to read. Sometimes the future of technology is wearing fur on an ice floe. Let's put it together. The polar bear vanishes on thermal cameras because its hollow, porous, aerogel-like hairs trap air and choke off escaping heat, no fiber optic tricks needed. Scientists copied that structure with free spinning, made it stretchy and washable, and knitted it into a sweater. And the same idea could insulate our buildings. Warmth without bulk, from a single strand of Arctic fur. It's worth pausing on the myth we let go of. The fiber optic story was gorgeous sunlight piped down glowing hairs to warm black skin. It was so satisfying that it survived in books for decades. But the truth turned out to be better. Not light, but trapped air. Not a light pipe, but an aerogel. The lesson? A beautiful idea isn't the same as a true one, and the truth is often stranger and more useful than the myth. Notice what's really doing the work here. Nothing. Empty space. The warmth of a polar bear, and of the fibers we've copied from it, comes from carefully arranged pockets of air from the voids, not the solid. We tend to think value lives in the material, the stuff you can touch. But here, the emptiness is the technology. Shape the nothing correctly, and it becomes one of the warmest things on Earth. Think about how strange this is. Usually, to get more of something, you add more material, more mass, more bulk, more weight. But the polar bear gets more warmth by adding less. More empty space, less solid. Its coat is warm because of what isn't there. Sometimes the best engineering isn't about piling on material. It's about removing it in exactly the right pattern and letting trapped air do the rest. And remember the scale. This isn't only about being comfy on a ski trip. Heating and cooling our buildings is one of the largest slices of humanity's energy use, and a big chunk of that is heat leaking through walls. A better insulator, deployed across millions of buildings, doesn't just save money. It means less fuel burned, fewer emissions, a lighter footprint. A trick from a bear's fur could be a genuinely planet-sized lever. And notice how it was found. Scientists didn't invent aerogel insulation from scratch and then discover the bear. They looked at an animal thriving in brutal cold and asked a simple question: how does it do that? That question, not a formula, led to the fiber. Nature has already stress-tested its designs for millions of years in the harshest conditions imaginable. It's the most experienced lab on the planet, and it's wide open. There's one more quiet lesson here. The people who debunked the light pipe myth weren't ruining a nice story, they were doing science exactly right. They tested a claim, found it false, and followed the evidence to something truer. And that truer answer is what gave us the fiber. Being willing to say, actually, that's wrong, isn't a weakness of science. It's the very thing that lets it move forward. It's remarkable how much was hiding in one hair. We looked at polar bear fur for generations and saw, well, fur. It took looking closer down to the hollow core and the porous walls to find one of the best insulators in nature. How many other everyday things are hiding a breakthrough at a scale we haven't bothered to examine? The world is full of answers, folded up too small to notice. We often picture advanced technology as hard and metallic chips, machines, steel, but some of the most powerful engineering is soft, light, and full of air. A polar bear's coat. A knitted aerogel sweater. An insulating panel light enough to lift with one hand. The cutting edge here isn't harder or denser. It's emptier and lighter. Sometimes the future isn't a stronger material, it's a smarter arrangement of almost nothing. Here's the thought to sit with. We spent a century engineering ways to stay warm, and an animal on the Arctic ice had quietly perfected it using nothing but trapped air shaped just right. We even told ourselves a pretty story about how it worked, and got it wrong. The real answer was better. Maybe our other hard problems have answers just like this one already solved, out in the cold, waiting for us to look closely enough. So next time you see a polar bear on a screen, in a photo, half asleep on the ice, don't just see a big white animal. See the best coat on Earth, woven from billions of hollow, air-filled hairs. And maybe, one day, the jacket that keeps you warm and the walls that keep your home cozy will carry the secret of that fur. Nature figured it out long ago. Our job is just to look and ask, why does this work? Thanks for watching. You're definitely a little smarter now, and you know one more story about how humans borrow their best ideas from nature.